Welcome to lesson 1.10, plant transport. Again, make sure to fill in your notes and highlight or star your vocabulary as we go through this lesson. So before we get into plant transport, we're going to need to introduce general cell transport, and we're going to learn a lot more about this in cell biology. Okay, but today we're going to kind of get the basics down. So there are two types of transport: passive transport, which is the movement of molecules across a membrane without using cellular energy, and active transport, movement of molecules against a concentration difference using cellular energy. So now we're going to discuss the different types of passive and active transport. Okay, so the types of passive transport, again, that is not using cellular energy. So we have diffusion, facilitated diffusion, and then a type of facilitated diffusion is osmosis. Okay, so diffusion is when particles move from an area of high concentration to low concentration. And then once the concentration of a substance on both sides of a membrane is the same, we call that equilibrium. Facilitated diffusion is molecules that cannot directly diffuse across a membrane pass through special protein channels. This still does not require any additional use of energy. For osmosis, the diffusion of water through a selectively permeable membrane. Okay, so osmosis is a type of facilitated diffusion because water passes through aquaporins, which are protein channels for water. Okay, so osmosis is a type of facilitated diffusion. So osmosis is just the diffusion of water. Okay, two terms that you need to know. You've probably heard these two terms before. Solutes are substances dissolved in solution. The way I remember this is I always think solute, sugar. For some reason, that's always just stuck in my head. The solvent is the substance that dissolves something. Water is known as the universal solvent. So in biology, majority of the time, your solvent will be water. So looking at the diagram below, here's an experimental setup. There is a barrier here, okay, and then there's starting off equal concentration of water on both sides, but on this side of the barrier, there is a higher concentration of sugar molecules or solutes, okay? So a general rule is water is always going to want to move towards higher concentrations of solutes. So what's going to happen is after it has sat there for a little bit, the water is going to want to move to this side or to the higher concentration of solutes. So a few terms that you need to know when talking about osmosis, okay? So a hypertonic solution, hyper, is when comparing solutions, it has a greater concentration of solute. If a cell is in a hypertonic solution, water is going to diffuse out of the cell towards the solution. A hypotonic solution is a solution with lesser concentrations of solutes. So in this case, water would want to diffuse into the cell. An isotonic, or equal, is a concentration of solutes is the same, okay? So if a cell is in an isotonic solution, there will be no net movement of water, or water will move in and out at an equal rate. So driven by differences in solute concentration, the net movement of water out or into a cell produces something that we call osmotic pressure. In plant cells, osmotic pressure can cause changes in the size of the central vacuole, which shrinks or swells as water moves into or out of the cell. So here's a graphic kind of what those rules look like. So generally, water will always move towards solutes. Water will move towards a hypertonic solution, and water will move away from a hypotonic solution. So looking at a plant cell and an isotonic solution, water is moving in and out at an equal rate. Plant cell in a hypertonic solution, water wants to move out of the cell, or wants to move out of the cell towards the solution because it has a higher concentration of solutes. In a hypotonic solution, water is going to want to move into the cell, okay? Or because the cell has a higher concentration of solute, water is going to be attracted to the inside of the cell. So water comes in and the cell will expand. Now, on to active transport. So, active transport is the movement of molecules against a concentration gradient using cellular energy. So, two types, molecular and bulk transport for active transport. For bulk transport, there are two types, endocytosis and exocytosis, and within endocytosis, there are another two types. You don't have to remember all of this yet. This is going to be brought back for our cell biology unit in Unit 3. So for now, just understand active transport uses energy. Small molecules and ions are carried across membranes by proteins in the membrane that act like pumps. And many cells use protein pumps to move calcium, potassium, and sodium ions across cell membranes. So here's kind of a diagram showing that pump that would be within a membrane and molecules having to be pushed across that using energy. So now that we've gone through the types of transport and you have the definitions down, I wanted to kind of provide a visual so that way you can tell the difference between the types. Also, I kind of like to tie in this fun like school analogy as we go through it. So for this part, you do not need to take notes. I'd rather you put your pen or pencil down and just kind of sit back and watch. So what's really cool about this is molecules are often going to behave kind of like people, specifically students, teachers, kind of that school environment. So for diffusion, okay, this first example, imagine this black box is my classroom. Okay, so we are students, here's the classroom. Okay, I pushed all of my students to the left side of the room in really tight, close quarters. So at this point, everybody's feeling extremely uncomfortable and they're like, Miss Hill, what are you doing? But I had told them all, okay, now you have to stand in this corner. Now, you as a student in the corner of the room, really close next to other students, what is your first thought? Your first thought is probably, I need to move away, I want my own space, I don't want to touch other people. So, requiring no brain energy, my students are going to want to move and disperse. And here they go. So, as students, again, diffusion is just moving from an area of high concentration to low concentration, or basically spreading out. It requires no energy, and it is a form of passive transport. So by the end of it, after all my students have spread out, they're going to be nicely distributed around their classroom. And if I were to divide my classroom in half, you would notice there'd be an equal distribution on both sides, okay? So that is essentially diffusion. Area of high concentration to low concentration, no energy, no brain power is required. Next one, facilitated diffusion. So the only difference between diffusion and facilitated diffusion is a protein channel. So here I have my students, okay, my hallway, also known as a protein channel. Okay, all of my students have free reign of my classroom here and the hallway to the outside. Okay, so I say, students, today you can move and work wherever you want. So naturally, all my students that were packed in my classroom are going to want to move out and they're going to want to spread out. Again, this is still not requiring energy. Okay, they spread out naturally. They're going from a high concentration to a lower concentration. And even within my classroom, they are now spreading out. Oh, and this last guy chose there. Okay, so facilitated diffusion, high to low, no energy. The only difference is you are adding in a protein channel. Now osmosis. The only difference between osmosis and facilitated diffusion is your protein channel is now an aquaporin, okay, so that's the name of it, and the molecules, the students, are now water. So the only difference between facilitated diffusion and osmosis, again, is aquaporin is the protein channel, and the students or the molecules are just water. So as they move, it's going to be the exact same thing that just happened, but I made the students blue just to show, again, it is water. And they spread out nice and even. And now all the students or water molecules are happy because they are balanced. So again, osmosis, passive transport, is a type of facilitated diffusion. Okay. So now whenever we add in solutes or dissolved substances in water, the rules of osmosis get a little bit different, Okay, so remember, this one that we just went over, we were dealing with no solutes. There was nothing in the cell itself or in the classroom itself. Water is just going to evenly distribute. As soon as you start adding in solutes, that game is going to change a little bit. So here, okay, new scenario. The hallway is still an aquaporin. Okay, now my classroom is a cell and it has water molecules in it. Okay, and then my students find out there is free candy outside. Okay, so there are my students, and there's the candy, all those pink boxes. Okay, so here are all my students. Within the cell, within my classroom, I always keep a little bit of candy, so, there's going to be some candy distributed. But the students find out there is free candy outside, and there is a lot of it. Okay, so this side, outside, would represent a hypertonic solution. Remember, a hypertonic, hyper means above, so it has a higher concentration of solutes, in this case sugar or candy, outside of the cell here, okay, than inside of the cell. So there's more candy on this side than on this side. So what do all of my water molecules or students want to do? Well, naturally, they want to get some candy. So they're going to all start leaving my classroom, going into the hallway. They're going to find their candy. They're going to bond to it. And they leave really fast. Okay, so, oh, and there's my one student left. My one student bonded to that one candy. All my other students left towards the hypertonic solution or the higher concentration of solutes. So what's going to happen is, now that I only have one student in my classroom or one student in my cell, my classroom size is going to shrink. Okay, so the classroom or the cell will shrink now that it's lost all of its water or students to the candy rush. Okay, so my classroom's going to shrink. All the free candy outside, my students are gone, water molecules are gone. Okay, cell has shrunk. Okay. Next scenario, this is an isotonic solution. So in this case, both my classroom and the outside of my classroom have equal amounts of candy or equal amounts of solutes, okay? So what's going to happen is my students here, they're pretty happy, they're balanced. What may happen is some students may kind of go back and forth, but you notice if one water molecule or one student leaves, another one's going to come back over. So there's going to be equal distribution of water moving back and forth, okay? So an isotonic solution, neither my classroom, the cell, or outside is going to expand or shrink. Water molecules are just simply going to go back and forth in a net movement of zero, okay? So if one goes over here, one's going to come back. Okay, now last scenario. So you still have your hallway. Now my classroom has the water molecules and I refilled my candy jar. Okay, so I have like my normal amount of candy, and yes, I do keep candy in my classroom. Okay, so what's going to happen is there is limited candy or limited solute outside in the hallway. So here are all of my students. Here are my candy storage, which are secret, okay? And then here are all my students, previous students out in the hallway, okay? So my previous students, they know I keep candy in my classroom, or they know that I have candy in my cell. So what all of my previous students are gonna do is they are going to want to come into my class, and my students are gonna wanna claim that candy. So water molecules are gonna bond to it, but here comes all my previous students. They're coming in, they're claiming their spot, they are all getting the candy, and then a couple find out in the hallway they're going to stay there. So by the end of it, my classroom, all of my previous students, current students, they all rush into my classroom or into the cell to bond to candy or bond to the solute. So this over here, the hallway, would have been a hypotonic solution. Okay, meaning that there was less concentrations of solutes or less candy in the hallway than what was in the cell or in my classroom. So all the water molecules rush to this side. Now what's going to happen to my classroom or cell? It's going to have to get way bigger to accommodate all of my new students, okay? So my cell is now this giant square here. It has expanded, so that way it can accommodate all of the new students. And then within this cell, these water molecules, these students attached to the candies, they would spread out as well. So kind of a fun thing to try at home. If you would like to try this, this is kind of seeing that in real time. If you have some gummy bears and water and or salt water, you can try this. So my first example, this would be a normal cell. This is a normal gummy bear. Okay, this was placed in an isotonic solution. You notice that it still looks the same. The net movement of water in and out of that gummy bear was equal. Okay, so that's going to be a normal cell. Now, if I put my cell or my gummy bear in distilled water, what happens to it? Well, it expands. All of the water that was surrounding this original gummy bear knew that there was sugar inside of it, so all of the water wants to go into the gummy bear, okay, and it's going to expand. So this would be a cell in a hypotonic solution, and oftentimes hypotonic solutions will be distilled water because water is going to want to move into the cell. It's going to expand that cell. And then the last one, I know kind of at first look this actually looks larger than this. I just think the picture is distorted. But this last one was the gummy bear in salt water. Okay, and it was a very, very high concentration of salt in the water. All of the water that was in the gummy bear moved out of the gummy bear to be into the salt water. Okay, because the water was more attracted to the higher concentration of salt outside of the cell rather than inside of the cell. So water would move out of the cell and it would shrink. That would be a cell in a hypertonic solution. Now, last one, active transport. So there are many different types of active transport. For now, you just need to understand the basic definition. Okay, so here's the hallway, and now it is also a protein channel or a pump. Okay, so the only difference is now this protein channel has a pump. Okay, it has some energy involved with it. Okay, here's my outside area with less molecules and ions, and there's my classroom. Okay, so in my classroom, it's full. I have a lot of students, okay? So full classroom or cell full of molecules, ions, or students, however you like to think of them, okay? Now here is the outside area, and obviously there's a little bit more room and less people. So naturally, all of the molecules or ions or students out here, they don't want to go back into a crowded classroom, okay? That is against their concentration gradient. That's going to require some energy, okay? But I am telling them, get back in class. You have to get back in class, get out of the hallway. So I have to apply some energy, okay? And then using my energy, I am going to make all of my students go against their concentration gradient or against what they want to do. And I'm going to have them go through that protein channel, pump them through, and I make them all go back into that crowded classroom. Now these molecules, again, they have to go against their concentration gradient. They have to be pushed to get back into this crowded classroom by a protein channel or pump. So now that you've seen a few examples of those types of transport, now we're going to get into plant transport specifically, or how things are going to move within the plant. Okay, so recall that the function of roots is to support the plant, anchor it in the ground, store food, and here, what we're going to be discussing today, absorb water and dissolve nutrients from the soil. Active transport brings the mineral ions of dissolved nutrients from the soil into the plant. The high concentration of ions is going to cause the water molecules to move into the plant by osmosis. So here's a diagram, or a small cross-section of a root. Okay, so again, active transport is going to cause the minerals. So this red arrow, you can follow here, minerals. So active transport is going to pump those minerals from the root hair all the way in. And then because the ions are being pumped in, water, remember, naturally wants to follow ions. So water is just going to follow those ions in, okay? So once water and dissolved minerals move past the inner boundary of the cortex, they're going to move towards the vascular cylinder. Okay, more water is going to follow, and that's going to create root pressure. And since water can only move upwards after passing the strip, a waterproof zone, water will move through the vascular cylinder into the xylem, then throughout the plant. Root pressure is the starting point for the movement of water through the entire plant. For our first check for understanding, go ahead and pause here and try to answer these on your own. So number 1, water is the universal solvent. Number 2, what is an example of a solute? There are many answers, 2 very common ones that we use in biology, salt and sugar. Those are dissolved. Number 3, what is the major difference between active and passive transport? Use of energy, right? Active uses energy, passive does not. Number 4, water tends to move towards the hypertonic solution or a solution that contains a greater amount of solute. Number 5, how are ions transported into roots? Ion transport is active. And then number 6, what type of transport causes water? That is passive, specifically osmosis. And again, that is because the water is going to follow the ions. And number 7, what is the driving force in roots that causes water to move throughout the plant? That is root pressure. Now for plant transport, continuing with water, okay, so once water has entered the roots, other forces involving multiple plant systems move water throughout the plants. The major force of water transport is transpiration, which is the evaporation of water from the leaves. Water is pulled up through the xylem. The tendency of water to rise in a thin tube is called capillary action. So in this diagram, this shows capillary action. You can kind of think of whenever you have a drink and a straw in it, generally the level of fluid is going to look a little bit higher in the straw than it does in the actual drink or the cup itself. Okay, that's just that tendency of water or liquids to rise in a thin tube. The interacting combination of transpiration and capillary action transports water throughout the xylem tissues of a plant. So next, for plant transport and nutrients, there's something called the pressure flow hypothesis. That explains that when sugars are pumped or removed from the phloem tissue, that change in concentration causes a movement of fluid in the same direction as the sugars. So in more detail, active transport moves sugars into the sieve tube from surrounding tissues. Water will then follow by osmosis, which is going to create pressure in the tube at the source of the sugars. And then sugars are actively pumped out of the tube and into the surrounding tissues. And again, water will always follow those sugars. Now for your exit ticket. Go ahead, pause here, answer these on your own. So number 1, what 2 forces were responsible for 90% of the upward flow of water? That is transpiration and capillary action. Number 2, what's the difference between diffusion and facilitated diffusion? Remember, both are types of passive transport, but facilitated diffusion uses protein channels to transport molecules across a membrane. Number 3, what's the difference between diffusion and osmosis? Osmosis is just the diffusion of water. It is a type of facilitated diffusion. Number 4, what type of transport typically moves ions across membranes? That is active transport. And number 5, what's the hypothesis that explains the movement of fluid through the phloem in a plant? And that is the pressure flow hypothesis. So now that we've gone through this lesson, go back, review, make sure you have your vocabulary terms down. Feel free to reach out with any questions. Thank you for listening.